Okay, so here we've got a lift with two boxes on the floor of the lift, one on top of the other. There's a light and extensible cable, and we're told the acceleration with which the lift is descending, so it's going down. So first thing I need to do is find the tension of the cable. So to do that, I'm going to model the lift just as one body, the lift and its contents combined. So there's the lift, there's the cable, so there's going to be tension in the cable. I know it's accelerating downwards with an acceleration of 1.8 meters a second squared. And then if I do the total mass of the lift and its content, so there's the 1,700 kilogram mass of the lift, there's 110 kilogram mass of block A, and 190 kilogram mass of block B. So altogether, the mass of the lift and its contents is 2,000 kilograms, so the force due to that is going to give us a weight of 2,000 G. So if I use F equals ma, and I'm taking down as positive, so the total force down is 2,000 G minus the tension in the lift, which is the total mass times the acceleration of 1.8. So if I do 2,000 G minus 2,000 times 1.8, and then I do the other side, I get T is 16,000 newtons. Okay, right, then it asks me about the force exerted by box B on box A. So to do that, I'm just going to look at box A. So there's box A, and box A is on the top, so there's nothing resting on box A. So for box A, we've got the weight of the box itself, so that's 110 G, and then we're going to have the force exerted on it by box B. So it's resting on top of box B, so let's call that subscript B. Okay, so just something to show that there is a force acting on box A by box B. Because if there was no force, then box A, if the only force on box A was its weight, then it would be falling with an acceleration of 110 times 9.8. And we know it's not. We know its acceleration is, sorry, it would be falling with an acceleration of 9.8 meters a second, and we know that it's falling with an acceleration of 1.8 meters a second. So there must be some force exerted by box B that's slowing it down. So this is part B. So if I use F equals ma on box A, again, I'm going to take down as positive. I know it's accelerating with an acceleration of 1.8 meters a second squared. So downward force is 110 G minus this force due to box B, and that must equal its mass times the acceleration. Okay, so 110 G. So 1078, and then if I minus 110 times 1.8, so minus 190, and if I add that force due to be over the other side, then I get 880 newtons. So that's the force on box A due to box B. Okay. Then I'm asked about the force exerted by box B on the floor of the lift. So to answer that, I'm just going to model the lift itself. So if I just look at the lift, okay, so there's tension in the lift, there's the weight of the lift, and then there's the force. So we've already used FB, so let's just call that force B. Right, so, and I know that the lift is, so I'm trying to get that thing out of the way, there we go, right. So I know the lift is accelerating down with an acceleration of 1.8 meters a second squared. Okay, oh sorry, I've got that, let me just correct that, I've got that going the wrong way. So I'm looking the forces on the lift. So box B is exerting a force downwards on the lift, isn't it? Right. That would help. Okay, so we use F equals ma again. I'm going to take down as positive. So looking at the forces on the lift, and I know from my previous answer that the tension is 16,000 newtons. So total forces down are 1,700 G plus B, which I'm saying is the force due to B, minus the tension, which I know is 1,600, and that must equal mass of the lift times acceleration, which I know is 1.8. Okay, so B is going to be 1,000. Oops, I've got an extra zero there, haven't I? Let's just cross it out, right? It should only be 1,700, right? So 1,700 times 1.8, so 3,060 plus 16,000 minus 1,700 times 9.8. So that force due to B is 1,60 plus right, sorry, just messing around with my calculator, right, is 2,400 newtons, and that's the force that B is exerting on the lift.